Hey Eric, I just thought it might be more helpful for me to just record something for you rather than try to explain via email, which I think is hard sometimes. Okay, so let's imagine we're trying to determine the charge on a cation and an anion. So let's say we have lithium fluoride. Okay, I know that lithium has one valence electron. Okay, normally it's neutral. It has 3 protons, so 3 protons, which are +1 times 3, so +3. And then as when it's neutral, 3 electrons, which are -1 plus 3, which is -3. So if I sum all of the subatomic particles in the nucleus of a lithium atom, the sum is 0, because I have as many protons in the nucleus as I have electrons on the outside. Fluorine is element number 9, so it has 9 protons. So this is going to be it's 9 plus 9 and 9 electrons. Right, so it is also neutral when it is an element in its elemental form. But let's say that I put lithium and fluorine together. And so I know that there's this one, oops, that's just a dot. Here's the 1 electron on lithium, right? That's the furthest, that's its valence electron. It's furthest away. And that's the one that is going to do chemistry. It's going to do chemistry. And lithium has 7 valence electrons. So, or sorry, fluorine has 7 valence electrons. Show it this way. And it has sort of room for one more in its valence shell. So what's going to happen is when I put those two substances together, the sort of combined sort of pull from the nucleus of these like 9 protons on this electron, it's enough because this one is held really loosely on here because it has a low ionization energy. This like huge pull, the electrostatic attraction on this fluorine atom, because this is a really, really small atom, so the protons are like right there, is enough to completely rip this off. And it goes all the way over there, right? And so now lithium is left with 2 electrons that are closest to the nucleus, and now this electron that was previously lithium's is now on fluorine. So now if I'm going to consider now the charge on this ion now, I'm going to say it still has 3 protons, so +1, and there's 3 of them, so that's +3, but now it only has 2 electrons because it lost one. So now its charge is +1. And what that charge is coming from, where it is like there's one proton in the nucleus that is unpaired, right? It doesn't have something neutralizing it on the outside of in the electron cloud. So it's really the charge of this one proton, and it's fully positive because that proton is completely exposed now. Now fluorine has an extra electron. So now we're looking at 9 protons, so +1 times 9. Again, we're not ever going to mess with protons. But now it's got 10 electrons. All right, so this is -1. Now the charge that I'm looking at that contributes to the charge on the fluorine is that extra electron, is that extra electron now from fluorine. So it is fully negative, right? This electron is completely off of lithium and on to fluorine. So it is fully negative and lithium is fully positive, okay? The negative charge comes from this electron and the positive charge comes from that proton. Okay, now let's imagine that we have something a little different. Let's say that we've got, and I don't, well, yes, I do. Let's say, like, if we're looking at a hydrogen and an oxygen, for example. So hydrogen and oxygen. Now, neither one of those two atoms has enough like pull capacity to like rip electrons off. Like there's neither one of them that has much stronger of a pull than the other. Certainly not enough to rip off an electron. In addition to that, they're all kind of holding onto their electrons. So like neither one of them has enough pulling power and they're all kind of like hanging onto their electrons. So rather than pulling them completely off, they're just going to like shift. They're going to like spend a little bit more of their time. So remember that I have hydrogen here with its 1 electron, And let's say I have a oxygen, and oxygen is actually going to form, looking like with water, it's going to actually do this like twice because it needs one right here and one right here. So let's actually move this one. Let's move one here and one here. So it's got room for two because it's got 6 valence electrons. 1, 2, 3, 4, 5, 6. And let's put another one over here. Now, what's going to happen is that because oxygen is more electronegative, it's going to, when these guys start to get a little closer, now the electrons in the valence shell, so here's oxygens and here's hydrogens, right? Now they're both using that shared pair, right? But because oxygen is pulling it a little bit closer to it now, so now I've got this proton here in the nucleus and this guy's proton here, but I'm not fully removing that proton. I'm not fully removing this electron and giving it to oxygen. I'm only kind of like taking it away sometimes. So like sometimes, most of the time, in fact, it's going to be spending its time closer to oxygen than it would to hydrogen. So like it's not fully positive because I'm not fully removing that electron. So it's only what we say partially positive because some of the time, most of the time, it's spending its time closer to oxygen, but not all the time. And so it's not fully negative, oxygen isn't fully negative because some of the time the electron actually is spending its time closer to hydrogen. So we call that partially negative. Now, the partial comes from the fact that sometimes this electron is like over here and sometimes it's over here and sometimes, so it kind of moves, but like most of the time statistically that electron pair is a little bit shifted closer to the oxygen. Okay, so this density we say is shifted most of the time closer to the oxygen atom, but it's not fully removing it. It's not fully taking away hydrogen's electron. It's only partially taking it away. It's only taking it away sometimes. And so we can't give that electron fully to oxygen, or we can't fully take it away from hydrogen. It's like sharing it. So like it's like if you're playing with a toy and then like someone has it someone might have the toy most of the time, but sometimes you have it. So you can't fully give it. You're not going to fully assign it to one person or fully take away from this person just part of the time. Okay? So that's why when we're looking at in terms of electronegative, I was calling it a hoodie. So like you've got this like proton in the nucleus of hydrogen. Well, like imagine you've got like a hood on that, and you're sort of like taking it part of the way off, but not all the way off. So like some of this sort of positive charge is able to sort of like seep, out, past that electron cloud, but not the full sort of proton's electronegative strength is able to like permeate space. And this electron is not fully attached to oxygen, so it also is not fully assigned to oxygen. So that's why I kind of call it like a hoodie. I know there's like memes where they have like Kermit with a hood on, and that's always what I think of, like Kermit the Frog. Anyway, okay, I hope that helps. It's like kind of, hopefully makes sense. But you're always going to, you're talking about shifting an electron back and forth. So we're talking about kind of removing it and partially exposing the proton on the least electronegative atom, and then partially giving that negative charge from that electron to the more electronegative element. And like how far it's shifted one way or the other determines the degree of polarity in that bond. If it's right smack in the middle, it's not polar at all. There's no partial charge. It's like they're both the same. But if it's like partially shifted, then it's like partially charged negative, partially positive. And if it's fully off one of the atoms, the metal, and given to the non-metal, then it's 100% polar. Okay? That's it. That's all I got.